Hello, community! You are coding LLMs and you feel you're always doing the same old thing? Welcome to a new idea. We look at fractals that appear within our large language models and how to use here the power of fractals to accelerate our LLMs. You might now be amazed and you say, no, that's not possible. The human language with a 0.7 and mathematics only a 0.5. Who calculated this? And you know, it was hydrology Hurst in 1951 while he studied the Nile River flooding. And this has such an importance today when we have here computational linguistics. So, to answer your question, is there something behind our LLMs? Is there some new insight we can get? Yes. So let's explore together. For my little green grasshoppers, hello there. So there are some terms that you might not know if you're new to computational linguistics. So here in green, you have the long-range dependency declared. Then we have here a measure for this. This is the Hurst parameter, this H that I just showed you. And you see that Hurst here, the classification. And these are statistically important, statistically benchmarks. Now, you know, we had the old Zipf's law and we had the old Heap's law in statistics. And you know that it is here in the new computational linguistics. This is some old stuff, and there are some problems with this. So what is now the new idea we can use? Now, of course, you read here in 2012, July 2nd here in PNAS, the origin of long-range correlation in human written text. And they explain how the long-range correlation flow from a highly structured linguistic level goes down to the building blocks of a text. Some beautiful insights, and now we use this in computational linguistics. So we use here something like a self-similarity of the human language. And, of course, you notice we are now looking at the computational linguistic insights. If we focus here on the fractal nature, do we have this in human language? And how can we use this to improve our accuracy, our reasoning for our large language model? Now, here you have some additional information if you want to read it in detail. But, and this is important, self-similarity in itself is not sufficient for a predictive language model to exhibit anything that resembles something like an intelligent behavior. Because for an intelligent behavior to manifest, the process must have some degree of predictability or dependence. And you might ask, hey, can you give me the absolute definition of this? Yes, absolutely. So systems should consistently respond to similar inputs in similar ways, allowing here for the learning of an autonomous system and the adaptation over time. The classical metric for quantifying this predictability in a stochastic process is the Hurst parameter, the H that I showed you at the very beginning of this video. And now you understand here the beauty and the importance of these two parameters. Let's dive deeper. If we have now a more formal quantification here of the terms we're going to use, of course, you know, we have here the self-similarity Hölder exponent. Hölder exponent statistics analysis, yes, you know this, and I ask here ChatGPT-4 to provide us here with a beautiful overview, gorgeous. And then, yes, we already mentioned it, a stochastic process. And here ChatGPT tells us here what is a stochastic process, the key characteristics, and the types of stochastic processes we're going to encounter. Remember random walks? We talked in my last video about random walks. Of course, we have discrete time processes and continuous time processes. So if you want, read this. Beautiful, some new insights. And now we formulate our new idea. We say the human language we view now as a stochastic process, where the sequences of the language units, the word or the phrases that we use, are converted in numerical sequences that represent linguistic features or properties. And then it examines how these sequences scale when observed at different magnification, especially looking for patterns that repeat across different scales. So what we are looking for is if human language exhibit a fractal-like property. And we use all the knowledge that we have and all the new publication. And if you think, heaven's sake, who did this? Google DeepMind and Google Research published this in February 2024. Fractal patterns may unravel the intelligence in the next token prediction form of a self-attention mechanism in the transformer network of large language models. Absolutely fascinating. Now, you know, of course, the self-similarity from Kolmogorov in 1940, and you know the fractals, the Mandelbrot set in 1982. But here now the insight is, and they established this with a beautiful paper on Archive. Here's the link. Go there, read it, some nice insights. And they say, hey, we establish as the authors of this paper that the human language is self-similar. And it is exhibiting complexities at a specific scaling with no particular characteristic context length. This will be important for, yes, you know, the context length. And we do have a long-range dependence, as I showed you, with an age of 0.7. This is now fascinating, because now you understand what this means. That mathematics lack an LDR, but human language, my goodness, this is a fractal structure. Human language contains fractals that we can use now in computational linguistics to understand and then integrate in our LLM training to get a better training result for our LLMs and vision language model and robotics models. So now let's talk about fractal large language models. Finally, we can talk about self-similar structures that live between the dimension in the Euclidean space. Yes, for my little green grasshoppers, yes, now I'm familiar with these terms. If you're new to AI, here I explain what are fractals. You know this as complex geometric shapes. What is here the self-similarity here? They appear in many areas of science, physics, biology, geography. Beautiful. Then I explain here for you the self-similarity. Please note the self-similarity can be exact or a statistical measure. And without self-similarity, a complex pattern would not qualify as a fractal. And not all self-similar structures are fractals. Think about these Russian dolls inside a Russian doll that has a Russian doll inside, these Matryoshka dolls. And some other insights for you to read. Now, one of the interesting questions here that we have to add is, if we go from a non-integer fractal dimension here, when we look at human language, and in my last video, I introduced you to the complexity classes that we have when we try to improve the logical reasoning of our LLMs. What is exactly the dimension, the correlation between the fractal dimension and the complexity class? Well, they found it. The fractal dimension is a quantitative measure of the complexity of a fractal object, indicating how the detail in the pattern changes with the scale at which it is measured. This is now interesting because we want to understand here the complexity of the human language. And if we can take care, or if we use this fractal nature of the human language for us, to improve how LLMs like Gemini Ultra or GPT-4 learn and generate text by this next token prediction. If we understand that there's more than this next token prediction because we have the fractal nature of our language. Now it gets interesting. So this inside implication, improving the design and training of LLMs. Yes, beautiful, you got it. What are the main insights if you read now the complete archive preprint here? Allow me to try a summary. They established a self-similarity and long-range dependency here in the human language. This implies that language patterns that we use as humans at any scale are indicative of those at larger scale, facilitating here a language model's ability to predict future tokens by understanding past and present context at various levels of granularity. Remember in my last video I showed you up here a new context evaluation benchmark by Apple? Doesn't it fit beautifully? Well, what a coincidence. B. Implication of LLMs. The LLM ability to predict the next token in a sequence is not merely a result of the learning of specific patterns in the pre-training phase, but it also stems here from their capacity to recognize and replicate the fractal nature of human language. This is new. This is something that should amaze you, because this is now a hidden pattern behind a hidden pattern. So, this capability enables LLM to perform tasks requiring understanding of the context and intent over varying length, thereby contributing to the intelligent behavior. If you analyze this, if you benchmark it, we go now beyond the perplexity, because now we include fractal parameters in our quest to understand here the power of our models, like the Hurst parameter or other parameter that they found, beyond the traditional perplexity-based metric. So, incorporating now the fractal dimension into the performance metric of our LLMs gives us a better understanding. And I will show you why we need this. Because exactly here, we can now establish a new training regime for the pre-training of our LLMs. In my last video, I only was talking about these complexity classes, the dependencies between an ICL prompt and a pre-trained and a fine-tuned LLM, that you should have a semantic, analogical, and a complexity coherence between those elements. Now we go a step further. Understanding LLM's fractal structure can improve the design and evaluation, contributing to more efficient and effective models for natural human language processing tasks. Interesting. Mathematics is special because, you know, the pile and the pile benchmark, and in the pile you have a mathematics subset. And if you here look exactly only, you focus here on the mathematics subset, you find that the Hurst parameter is exactly 0.5. And you remember from the definition of the Hurst parameter, this is important because this means an absence of a long-range dependence in the mathematical training text. And this is contrasting sharply with other linguistic human language domains that exhibit here some significant long-range dependence. And you know, this long-range dependence is a measure of the persistence of correlation in the data across different scales. So, absolutely fascinating. They try to explain this, that unlike our natural human language, which relies on contextual and flexible usage of word and grammar, the mathematical language is much more precise with symbols and formulas that follow here very strict rules. And this very special Hurst parameter in the mathematics domain suggests that the mathematical text behaves more like a random walk. You remember? Stochastic system? Yes, random walk, where each element, so each mathematical theorem or each mathematical equation is largely independent of others. And this independence is a reflection how the mathematical concepts are often presented. Each theorem and each definition is self-contained. So the beauty of mathematics suddenly finds an expression here in our Hurst number. This means that unlike our human natural language, where you have themes, motive, linguistic structure that recur at multiple scale, those mathematical texts that LLMs have so much problem to understand mathematical text do not exhibit the same fractal patterns. And here the logical and the hierarchical nature of mathematics mean that while concepts are interconnected, they do not repeat or scale in the way that our human linguistic patterns do. This is fascinating. And for me, my syntax is now, do not use large language model pre-trained on a fractal human language for non-fractal mathematics. Okay. Another funny thing, and this is now green for my green grasshoppers for the young community. If you start and you look at GitHub and all the code you'll find over there, now this is simple because Google calculated the horse parameter here for GitHub and they find it high, 0.8. And this implies that all the code examples process here a degree of self-similarity and persistence over long sequences, which is really indicative of the structure and hierarchical nature of the programming languages that we use, like Python or C++ or whatever you have. So you see, those structures are reused across different parts of a code base. And it's true, if I code something and I have just a short code snippet, I have here my familiar structures. I don't know, 20, 30, maybe 40 different alterations that I use. But I also have self-similar patterns if I scale up and scale up even more. Interesting to see here this. So this means software development frequently employs here design patterns that they follow, which are generally reusable solutions to common problems in the software design. Interesting, if we now apply an AI that should here simulate here or learns from the GitHub code examples, this should be really easy for an AI to learn because we have such a high fractal nature of our self-similarity in the code base. Okay, so here you have it now. Mathematics, beautiful. Human language, beautiful. A fractal nature, we have long-range dependencies, and as a measure, we have a fractal dimensionality, that lives between our natural numbers, between the Euclidean dimension. And then for pure code that we write, it is even higher. This explains now a lot of the problems we've had when fine-tuning, optimizing our large language model, because we have hidden structure, different hidden structure. If you optimize an LLM for mathematics, for simple human language, or for coding, CodePilot for pure GitHub. Interesting, if you look at neuroscience, there's this idea that our human brains might be inherently suited for processing fractal information due to the fractal patterns that facilitates here the chunking and the hierarchical decomposition of complex information from our sensors, from our ears, from our eyes, whatever, aiding here a comprehension within our given memory limitation. Think about here at the eye. And we have a self-similar organization of our neurons in our brain that could potentially, maybe under certain circumstances, resonate with the fractal language structure that we use, enhancing now the processing here of our human language significantly. So you see, those fractals emerge naturally in various complex systems, in biological growth inside of our body, suggesting maybe a deeper connection, a deeper connectivity between the way our neurons are structured in a self-similar way and how human language is self-similar. This would have some real massive implications for the universal computational principle that we use to mimic human language. This you can extend if you want, that this self-similarity allows for a quick encoding and decoding of recurring patterns, of recurring self-similar patterns, reducing now in the case of a human, our human cognitive load. But if you think about AI, we can now optimize our compiler complexities, and there should be some beautiful solution for the memory management that we currently need to optimize. Plus, if we talk about reasoning, those long-range dependencies can enable us to express complex ideas by linking distant elements much more efficiently when we model them in computational linguistic with fractals. So there are a lot of different questions I have for myself, and I want to show you where I'm currently. So I think there's a direct effect here on the pre-training data sets that we use to pre-train our LLM. And this includes here the context length for finding the fractal patterns, plus here the complexity classes. Remember that fractals, they live between our Euclidean dimension. I will show you this, we compute this in a second. Then, as I told you, I will not use now LLMs pre-trained on the human language now for non-fractal mathematic formulations. I have ideas about how to synthesize new data set, generate new data set here with a fractal structure, scaling the complexity for the pre-training. I have to rethink here this chunking of our text. Remember, a RAG system normally chunks here up the text about 100 token. I've seen some about 200 token. This might be the completely wrong way to chunk here our text, because maybe we should follow here more here the fractal defined pattern that we find in the human language, or in the specific use case that I will code. And yeah, the impact on the max token length, on the context length during the pre-training phase. There are some indication, yeah, that's a little bit too complicated, but there's a connectivity to the fractal complexity class. Okay. I went to ChatGPT 4, as you can see, and I said, hey, create a real simple Koch curve right from the beginning. Just go here with 4 iteration. ChatGPT comes back, Python, beautiful, and here, this is what you get. So this is your Koch curve. And now the fractal dimension of this Koch curve is, as we just find out, a measure of its local complexity. And you know, if we calculate this, the dimensionality of this curve is not 1, is not 2, but is 1.2619. This fractal dimension reflects the Koch curve's self-similarity and infinite detail, revealing how it occupies here a space between dimension 1 and dimension 2. So with the fractals, we live between the Euclidean dimensions. And there's a lot of space over there. Beautiful. By the way, if you want to look at this study, please note all the computation for the experiment by Google, they conducted in JAX and in FLAX, using here the open source T5X framework. I have some videos about this. Maybe you start here. Why the hell we need a third machine learning framework in 2023? Yes, 7 months ago. And I also explain here the T5X framework, and they use here the complete code examples. Great. Talking about code, I think it is important to show you, if you want to have a deep dive now in the coding of this, there's a beautiful Python library that makes it life so much easier. So topological X or topo X, whatever you want. So Python packages for machine learning on new topological domains. As you can see, February 2024, beautiful, beautiful publication. Have a look at the publication. They introduce here a Python software suite for some user-friendly building blocks of computing and machine learning in topological domains that extend here the graph the graph neural network that we know. We go now to hypergraphs, to simplicial complexes, to cellular complexes, new path and new combinatorial complexes. CW complex, I talked about this very shortly in my last video here, but we are here in algebraic topology. Now, algebraic topology, a beautiful branch of mathematics. If you want to learn more about it, there's a free source, a free book I would recommend, Concise Course in Algebraic Topology, 250 pages from the University of Chicago. And here you have the PDF link if you want to have a deep dive. But I guess you need a month for this book. But it depends on your mathematical skills. Beautiful. So here now the GitHub, you have here where I start topological, the netx, then you have the embedding x, and then you have the model x. Have a look at this, really beautiful. Where are we? Nobody there, 95 followers. Come on, we can do better. It is open source. Take advantage of this in a Jupyter notebook. Could not be easier. Beautiful. If you want to understand a little bit in my way as I explain this, I have 2 videos for you that help you here with understanding what's going on in the code. I have this video here, Discover the Future of Graph Neural Networks Beyond Message Passing, Beyond Graph GNNs here. And the second video is here about simplicial complexes in Graph Neural Network. So topological message passing here and simplicial complexes on CW networks. Yeah, what is a CW complex? So if you want to have a deep dive, if you find a new topic in artificial intelligence that you say, hey, I want it a little bit more spicy. I want to be excited about something new, not just training new hyperparameter for my self-kitted, I don't know, LLM. This is the way to go. Okay. What would be great, and this is my topic here for 2024, maybe you are the person to investigate here fractal attention. Because if we would be able to implement our knowledge, what we just introduced here about the fractal nature of the human language now in the computational linguistic, and then learn about this, how we can optimize our large language model, I think we will make a significant jump forward to improve our accuracy of our LLM, to improve on the training procedures of our LLM, especially the pre-training. But if we can utilize the power here of this fractal structure that we encode, we have benefits from memory management on our data center cards to unbelievable ideas. But maybe I tell you more about my ideas in the next video. I hope you found it interesting. I hope I had some new ideas that I could show you. It would be great to see you in my next video.